Today, it is about how we can holistically examine the acoustics in the electric vehicle and how to include measurement data in addition to the acoustic data in a synchronized manner. For example, currents, voltages, power, and temperatures, forces, vibrations, and so on. In other words, data that is relevant to the cause, effect, and optimization of acoustic phenomena. But first, what are the special challenges in the acoustics of electric vehicles? Let's take a look at the properties of the components in electric vehicles. First of all, there is the electric motor. In contrast to the combustion engine, it causes fewer oscillations, as we know, vibrations, and also less mechanical noises. Due to the quieter engine, however, other sources of noise came to the fore, and conceptually, the entire powertrain generates unpleasant tonal noises at higher frequency. So, and in addition, in an electric vehicle, for example, further up to 1,000 other noise sources operate. So, and such sources from transmissions, pumps, cooling systems, hydraulics, and power electronics are not expected by the passengers and can be disturbing. Transmission whine, electric motor wear, and the whistle of a converter are usually perceived as irritating. In addition, the components in the vehicle can resonate, and we hear a buzzing, wiring, ticking, hissing, and so on. And we perceive them as a deviation from the normal operation and may seek a repair service. During driving noise at higher speeds and tire rolling noise are becoming also more dominant. This is a particular problem with the now popular SUVs with large tires. In addition, the electric vehicles are much heavier, which makes the rolling noise louder. A premium BEV, for instance, drags 500 kilogram more death weight over the roads than a comparable combustion engine vehicle. So, and in summary, we could say that the different noise sources, also everything is quieter overall, be considered and optimized during vehicle development. So, and vehicle development therefore want to eliminate, mask, or insulate noise that does not match the driving situation. Because the acoustics inside the vehicle define the well-being, the comfort, and last but not least, also the purchase decision. So acoustic is the subjective factor for the perceived quality of a car. And therefore, the noise sources must be defined with measurements. For example, in a sound measuring room, acoustic or NVH test bench, and also while driving. So if possible, disturbing noises of the components should be eliminated also by improving the regulation and control, for instance, for the motor. But for this, however, the parameters must be measured, for example, the inverter currents that control the electric motors. And to meet these challenges, CSM and Müller BBM Vibroakustik-Systeme entered into a partnership last year. And at this point, I say some words about our partner. Müller BBM Vibroakustik-Systeme is a spin-off of the Müller BBM Group with a headquarter in Planegg, nearby Munich, Germany. Turnover and number of employees is comparable to CSM. And their core competence is in the area of testing and interpretation of dynamic physical data, in particular for the areas NVH, operational stability, and comfort. The tools are around the well-known PAC technology for data acquisition, networking for data networks, and data management with cloud services. So, what have we developed in our partnership and what are the applications we have targeted? Until now, The electrical high voltage measurements in the electric vehicles and the NVH measurements were performed with separate, non-synchronized measurement system. Manual time-consuming reworking is then possible, and also afterwards the comparison is necessary because simultaneous real-time measurements and NVH analysis are together not feasible then. But together, CSM and Müller BBM have integrated and synchronized their measurement system. This means that just with one measurement setup, with CSM measurement modules and the PAC-Live technology, dynamic data can now be acquired, analyzed, evaluated, and managed. The advantage of this solution is then the combination of the high voltage measurement and NVH, for example, the inverter currents with the simultaneous NVH analysis. And with PAC, you can easily record all acoustic quantities, and you are no longer blind to what is happening electrotechnically. Particularly in order to optimize the noise of drivetrain components, both have to be recorded synchronously. So we will now take a closer look at this in an example. We use a microphone array for the spatial level measurement on the head area. Here with a multimic from Müller BBM on the co-driver's seat here, it contains 6 microphones for measuring the sound pressure in the area of the head position. And the advantage of the multimic is as follows: so-called standing waves propagate in the vehicle interior. Such standing waves have nodes that hardly move, and this is particularly critical in electric vehicles because the frequencies are higher and the wavelength is smaller, and therefore it's crucial how you sit. If you are sitting with one ear in such a node, you might hear anything, but if you move away a little bit, you might hear a whistling. Yeah. Therefore, we measure with 6 randomly distributed microphones, a microphone error. Then you can be sure that you are not only measuring in one node. In this way, we capture all noises in the passenger compartment: driving noise, tire rolling noise, aeroacoustic noise, and all from other mechatronic components. And the microphones are connected to CSM AD mini modules and linked to the measurement PC. On this PAC-Live works on the measurement PC with customized analysis. So on the left, you see some examples here. With them, we define the sound sources and analyze the acoustic phenomena. And for instance, the tonality of the electric motor or other components in the vehicle. And to solve this tonality problems, we have to measure their origin at the same time. So current, voltages, and rotation, and so on. And this can then be used to make a change, for example, in the motor control in order to avoid certain tones. So how do we incorporate these electrical high voltage measurements in addition? And we take a look at this in a system overview. Classically, we have CAN measurement modules for measuring temperatures, pressures, and other physical parameters. We CSM both conventional and high voltage safe ones. Ethernet measurement modules are used for rapidly changing signals such as acoustic signals, vibrations, and accelerations. And here too, there are conventional and high voltage variants. High voltage breakout modules are used for measurements in the high voltage electrical system, with which currents and voltage and power in the high voltage lines, cables are measured. The CSM measurement modules are connected to measurement chains via CAN or EtherCAT. And they are bundled and synchronized via the XCP standard, either via XCP gateway or a XCP module with gateway function. So data acquisition is via the XCP on Ethernet interface to the measuring PC and the PAC system. The measuring chains are then connected directly to the PAC Live Hub. For example, the EtherCAT AD mini modules for the microphones and acceleration sensors. In the same way, CAN counter modules, for instance, CNT4 Evo to measure speed and torques. And with the different breakout modules, we measure directly in the high voltage lines, for instance, from motor and inverters. So, and CSM has developed the PAC add-on software to synchronize the measurement data with PAC. This makes the measurement data available to the PAC suite for analysis in real time. And here you see the measurement interface in PAC with which the measurement channels of the CSM modules are configured. So it differs not in terms of integration from other measurement channels. For example, if a PAC MK2 is also connected to the PAC Live Hub. In the vehicle, the measurement setup can then look like this. For example, a decentralized distributed measurement system with CSM measurement modules close to measurement points or to sensor points of the vehicle components and also in the high voltage lines, for instance. So the CSM modules capture everything that can lead to tonal effects. In the picture, we have limited us to an example in the drivetrain here, and the microphone array, which I have explained, is installed on the passenger seat. Also, the 3 PAC software components are installed on the measuring PC, so the PAC Live Hub, PAC 6.x, and CSM PAC add-on. And we now look at the motor and inverter measurements. And here you see a list of tests and analyses that are usually performed. And for these, we want to measure the currents and voltages in the drivetrain. As you can see in the figure, we use a high voltage breakout module 1.2 between the battery and inverter, and in the 3 motor phases, high voltage breakout module 3.3, and both measure currents, voltages, and power. And with this, the PAC suite can now analyze a PWM analysis, the order analysis, or the associated frequency bins of the spectra, or the necessary Clark, Park, and DQ transformations can also be performed. That means that the chain of effects, for example, of the motor control parameters for acoustic phenomena can be viewed. So, and just briefly, we take a look at the 2 measurement modules. The high voltage breakout module 1.2 samples current and voltage in the HV plus and minus line between the inverter and the battery. The power values of active, apparent, and reactive power are calculated in real time in the module. And the measured and calculated values are output via EtherCAT or CAN. The high voltage breakout module 3.3 is inserted into the 3 phases to the motor to measure the control currents. It also acts as an XCP gateway for direct connection to the measuring computer. That means that we can connect all other modules here to this module, for example, a counter module or the high voltage breakout module 1.2, also, for instance, temperature measurement modules. It handles also synchronization as an IEEE 1588 PTP slave. So now let's look at an analysis with the multimic. So the acoustic measurements in the interior we want to evaluate. We have the sound pressure level of the 6 microphones over time in Y direction. In addition, the frequency analysis in X direction. As usually, the frequency is displayed logarithmically in octave strips, octave rooms here. And we see the sound pressure colored in it here. And there is a red phenomena that could cause us a concern. So we see a recording the average sound pressure in the car interior over the octave bands at a time interval of 35 seconds. And at 250 Hertz, we have a tonal problem with a large sound pressure. And below the recordings of the 6 microphones in the octave band of 250 Hertz here, and each individual line is a microphone. And we see very clearly over the time the differences in the microphone curves. So for instance, at 40 seconds here, we see the turquoise curve very clearly below the others. The difference is about 5 dB. So at 6 dB, we would have already a doubling of the volume. So if you had measured the black curve, for instance, with only one microphone, made an optimization, and later measured it again with the same microphone on a slightly different place, for instance, the turquoise microphone's place, you could get the impression that the optimization would have made a difference. It must not be so. So let us look at another acoustic analysis that correlates with the engine power. We see a drive motor in its tonality here without corresponding acoustic arrangements. In the top measurement image, we see the power measurement of the electric motor. The motor is on a load or torque ramp, and we see intuitively that something is wrong, that cannot sound good when we hear it. We have noticeably unpleasant tones here. We see over time the engine orders. The orders go to the left. That means the speed goes down, the torque goes up. And we see that the orders go to natural frequencies. These are the straight red lines here. We see all orders go to natural frequencies and form peaks at these crossing areas. These are the dark red areas. Yeah, and these can now be further investigated. Yeah, and suitable adjustments can be planned. Can the motor control be changed in a way that the disturbing noises are reduced? Or does a suitable insulation with sound absorbers have to be installed? Yeah? Or is an active noise cancellation with an artificial countersound even necessary? So let's look at another example analysis on a powertrain, a recording with only one microphone, but again with built-in CSM measurement modules for power analysis. We see on the left the airborne sound, the total level, dBA in red here. And for acousticants, it's normal to record also the speed, the green curve here. We see that something is happening with the speed. It remains constant after ramping up and then goes up. It remains constant, goes down to the previous level, and then it's falling down. And however, what we also see here, this plateau, it has little effect to the overall level, the red curve here. So here we see the acoustic analysis for this purpose. The microphone recording shows various phenomena here. So after the run-up, the phenomena start. Let me draw here something. So about here and about here at 30 seconds about. We see that the phenomena start, and when it's going down, it's about here and about here, the phenomena disappear. And we see something else here, the overall level, the red curve here is not louder as mentioned here on the plateau, but still there's something what we subjectively perceive as a tonal noise. And yeah, the background is the total level is the sum of all energies and frequencies in the spectrum, but it does not really reflect what you hear. The specific tonal content is based on the hearing model, yeah, and man here according to Park scale, we could say with 24 selective microphones, and each analyzes a band. So in that case, we could interpret from a certain speed on, there are tonal noises here. This here. So to the speed, we calculate the mechanical power with a torque and add it to the interpretation. This is the black curve here. And now we see a power drop. And we see also here a zero transition in recuperation. So what we can now say, this is a recuperation process which needs further investigation. Yeah, and from this simple example, we see also only through holistic interdisciplinary views, we can do an exact interpretation of cause and effect. So, and with the Miller BBM measurement setups, the different signals can be recorded and correlated in a synchronized manner. Acoustic signals, electric, analog, and digital signals, or signals from rotating systems, oscillations, and vibrations. So here is a summary of the benefits that have resulted from the joint development of CSM and Müller BBM Vibro acoustic system. I have discussed most of them in the previous slide, but I would like to emphasize the decentralized measurement setup, which allows to measure directly at the acoustic components in the vehicle. And the incorporation of the measurement data into the powerful PAC technology, and then the correlation of the acoustic and electric phenomena. And this leads overall to an acceleration in testing, generally in development and also in optimization. So just here also an overview of what's necessary for this CSM measurement modules and the sensors to it, the PAC thick studied NVH software, the new software CSM PAC add-on, and this also for the XCP gateway, and for synchronization, the option PTP support.